In this last video, before we kind of close out the lesson, I just wanted to give you a preview of a couple of homework problems that you'll have. One of them, I believe, is in the bookwork. Actually, both of them are in the bookwork, but I put number 12 here on the Van der Waal question on a set of challenge problems for you. And the reason why is because it's in our new book. I took it from the new book before we had the new book. Does that even make sense to you? It doesn't matter. Anyway, so example 11, prove the power rule for rational values of n. To do this, let n equal p over q, where p and q are integers. Well, here, let me just kind of flesh this out just a little bit. The power rule, remember, goes like this. Derivative with respect to x of x to the nth power is equal to leapfrog n times x to the n minus 1 power, right? Right. But whenever we proved this using Pascal's triangle. This 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. But that only works for whole number powers. And we've been using it nonstop for things like to square roots for the 1/2 power. We've also been using it for negative powers. But that proof was, it was inadequate for those. We just assumed that it worked. So here with a chain rule, we are able to prove the power rule for rational exponents when you have square roots, cube roots, and stuff like that. So to do it, if I have my equation, which I'm going to write like this, y is equal to x to the n. But I'm going to rewrite it with this rational exponent that's right here, assuming that that's what I have. Y is equal to x to the p over q power. And now what I want to do is I'm going to raise both of these sides to the qth power. Raise it to the qth power. So when I raise the left side to the qth power, I have y to the q is equal to, and then x to the pq raised to the q power. You multiply those exponents together, you get x to the p power. There you go. So now on this thing, you want to use implicit differentiation. And then when you're all done, you want to solve it for just dy dx and show that that's going to be equal to this. Actually, wherever there is a n, it would have this in it. So you're trying to show that this is equal to p over q, x to the p over q minus 1 power, right? Okay, very good. All right, let's look at this last one, kind of sneak preview here. All right, in 1873, Johann van der Waals derived an equation relating the pressure P, volume V, and temperature T of a gas as where A, N, B, and R are constants. Find and interpret dV, dP. Okay, however, there's one extra variable in here, and that's T. So what we're going to do for the purposes of this equation and taking its derivative, you will treat that like it's a constant, as if temperature is not changing, okay? And then when you're all done, getting that derivative using implicit differentiation, because you're differentiating, this V up here is going to be like your Y. So it's your dependent variable. It's the one that is going to get the chain rule component. And P, the one that's down here on the bottom, it's like your X. That's the one that you differentiate normally, okay? And then whenever you're all done, what does this mean? What does dV, dP mean in the context of this problem? All right, so that should do it. That wraps up this implicit differentiation lesson, where we're taking the derivative of an implicit equation. It has x's and y's mixed in with the equation. When we're all done, we're going to get a derivative that's a function of both x's and y's. And in order to do it, I'm going to use the chain rule on anything that contains a y, because I'm interpreting that y as at least one function of x.